Section: Introduction. In this section, we explore how generative models for language, images, and video are reaching human-level performance. As these models generate a significant amount of training data for future models, concerns arise about the risk of model collapse, where training on machine-generated data may lead to a drop in model performance. This phenomenon challenges known scaling laws, where larger training sets do not necessarily improve performance when the data is synthetic. We investigate the use of reinforcement learning with human feedback, RLHF, to train models beyond their performance on internet data. By leveraging human feedback, we aim to improve model performance and prevent model collapse. Our theoretical analysis focuses on Gaussian mixtures in a high-dimensional setting, showing that selecting high-quality data points can lead to optimal model performance, comparable to training on original data. Through simulations on synthesized data, we demonstrate that human supervision in data selection consistently improves model performance compared to using original labels. This highlights the effectiveness of human-in-the-loop supervision in training models with synthetic data. Our experiments on tasks like arithmetic prediction and news summarization further support the importance of human supervision in preventing model collapse and enhancing model performance. In summary, our research emphasizes the significance of data selection in maintaining model performance when scaling up with synthesized data. By distinguishing high-quality data through human supervision, we can overcome challenges like model collapse and continue to improve model performance. Section Summary. In this section, we provide analytical results showing that selecting high-quality data from synthesized datasets can lead to optimal model performance, even surpassing training on original data. Through simulations and experiments, we demonstrate that human supervision in data selection can prevent model collapse and improve model performance, especially in scenarios like arithmetic tasks and news summarization. By leveraging reinforcement techniques and oracle supervision, we show that distinguishing high-quality data is crucial for scaling up with synthesized data effectively and avoiding performance degradation. Section: Theoretical Insights. In this section, we start by theoretically explaining when data selection with reinforcement can lead to improvements for a group of high-dimensional data distributions. We model the reinforcement process as a pruning strategy on created data. Importantly, we do not assume that the pruning strategy knows the ground truth. Instead, we allow for intermediate pruners in our theory, which can be seen as reinforcement from a different or the same model. A detailed explanation of our general theory can be found in the appendix. For simplicity, we focus on Gaussian mixtures here. Setting: Data distribution. We focus on distributions over features with specific high-dimensional concentration properties. A special case we consider is binary Gaussian mixtures, where features have a certain conditional distribution. Synthesized data. We have a dataset of pairs from the true distribution and synthesized data generated from the same distribution but with labels generated by an AI model. Downstream model and pruning. We model our data selection, with or without feedback, using a pruning strategy. For the downstream models, we consider a specific family parametrized by weights and a sigmoid non-linearity. The downstream classifier is obtained through logistic regression fitted on the data. Test accuracy. The test accuracy of the downstream model is defined for a random test point using the Bayes optimal classifier. We focus on how this accuracy depends on errors in the data generator and the choice of pruning strategy in the infinite sample limit. Pruning strategy. We consider a class of parametrized pruning strategies called RLHF pruning, which have the property that the pruning decisions are independent. We define a probability related to label disagreement in the synthesized data. In this section, we concentrate on a specific case of supervised pruning strategies that filter out examples with label disagreement. We also mention two other notable pruning strategies: no pruning, where the entire training dataset is used, and oracle pruning, where only examples with correct labels are kept. Performance of models trained with pruning. Insights from infinite sample regime. Our main theoretical result characterizes the test accuracy of the downstream model on pruned data as a function of label disagreement and the pruning parameters in the limit of infinite training data. The result shows a sharp phase transition around a certain corruption level. As the label disagreement increases past a certain point, the downstream model switches from being perfectly accurate to perfectly inaccurate. The proof involves computing empirical test accuracy and using concentration of measure techniques. This sharp transition is due to the infinite sample regime, where finite sample corrections are avoided. Section Summary. In this section, we theoretically analyze how data selection with reinforcement can enhance performance for high-dimensional data distributions. We model the reinforcement process as a pruning strategy over synthesized data, without assuming access to ground truth, allowing for various types of reinforcement models. Focusing on Gaussian mixtures, we investigate the impact of errors in the data generator and the choice of pruning strategy on the downstream model's test accuracy in the infinite sample limit. Section. Some consequences of Theorem 3.2. In this section, we will discuss some important applications of Theorem 3.2. These examples are supported by empirical evidence shown in the figures. Refer to the figures in the appendix as well. When we do not perform any pruning, with certain parameters, the downstream model achieves a high accuracy level for a range of corruption parameter values. This accuracy remains high up to a specific breakdown point as predicted by Theorem 3.2. In the case of oracle pruning, with different parameters, the downstream model achieves a consistent high accuracy level for various corruption parameter values up to a breakdown point as predicted by Theorem 3.2. This outcome is not surprising because even for moderately large parameter values, the breakdown point can still be close. For supervised pruning, we consider isotropic Gaussian mixture data with specific means and a pruning strategy outlined in an equation. The parameters are dependent on certain angles because they correspond to probabilities for a travariate normal distribution with correlation coefficients determined by these angles. When we look at decoupling the generator and verifier, although they are linked in supervised pruning, there are insights that help us separate them. A better generator always enhances performance. When the verifier is not reliable, such as in cases of no pruning or random pruning, a good generator is crucial for achieving good performance. Conversely, when the verifier is close to an oracle, the breakdown point is high, and any non-degenerate generator is sufficient. In simulations on synthesized data, we explore the practical implications of the theory by conducting simulations in finite scenarios. We examine how the generator and verifier impact performance and scaling rates concerning the number of synthesized data points. Following the theoretical setup, we use the same Gaussian mixture and linear models for the generator and selector. We introduce a fixed unit vector and a specific distribution controlled by a scalar that determines the overlap. To generate synthesized data, we initially sample data from a distribution to create the original dataset, which is then used to train a linear model. Subsequently, we generate additional data points using a specific method, forming the synthesized dataset. The data is selected based on certain parameters, and we run simulations with different values to observe the impact on performance. We analyze the performance under various levels of verifier accuracy, ranging from oracle level to different error levels. The simulations demonstrate the theory in practical scenarios, showing that oracle supervision leads to optimal performance. Improving both the generator and verifier generally enhances performance. However, we will later observe in an experiment that slightly increasing the verifier's accuracy while changing its correlation with the generator can sometimes have a negative impact on performance. In the experiments, we explore how reinforcement methods and the generator affect performance in different scenarios, such as training a transformer and fine-tuning a model for a news summarization task. Section Summary. In this section, we explore the consequences of Theorem 3.2 through various applications. We observe that different pruning strategies lead to varying accuracies in downstream models, with the breakdown point being a crucial factor. By decoupling the generator and verifier, we find that the performance is influenced by the quality of both components, as demonstrated in simulations on synthesized data, showcasing the practical implications of the theoretical framework. Section: Understanding the quality of synthesized data. In this section, we explore the quality of synthesized data. We focus on solving arithmetic tasks using a transformer model, which helps us assess the quality of the generated data since we can measure errors and compare them to the correct answers. The transformer is trained to predict the 5 eigenvalues of 119 by 119 symmetric real matrices based on 25 real entries. The data used for training, testing, and synthesis is created by randomly sampling matrices with independent entries from a 120 by 120 matrix. A prediction is considered accurate if the relative error in the predicted norm is below a certain threshold. The data generator is trained on around 200,000 examples using the Atom optimizer for 65 epochs before it starts overfitting. We emphasize the importance of selection in our experiments. When we increase the number of beams in the beam search from 1 to 50, the accuracy of the predictions improves significantly. This shows that the model has the potential to generate better solutions, but it struggles to choose the best prediction on its own. To improve the quality of synthesized data, external supervision is necessary. Moving on to generating synthesized data for arithmetic tasks, we collect more matrices randomly and use the generator to label them. We introduce a verifier that measures the difference between the model's predictions and the correct solutions. We experiment with 2 methods of data selection and label selection. Data selection retains only the data with correct predictions, while label selection selects the best prediction from a pool of possible solutions generated by the model. We create 7 synthesized datasets, each containing 1 million examples, using different selection methods and beam sizes. When training the transformer model with the synthesized data, we observe model collapse when using its own generated data, leading to a decrease in performance. However, when we incorporate external supervision through data and label selection, the model's performance improves significantly. Increasing the number of beams in the beam search also enhances the quality of the selected synthesized data. We further investigate the impact of using more data and stricter selection criteria on performance. By increasing the amount of data and using a stronger selection process, we achieve better results, aligning with our theoretical expectations. In another experiment on news summarization using Llama 2 to 7b and Llama 3 to 8b models, we fine-tune the generator on a subset of the XLSUM dataset. We evaluate the model's performance using the Rouge 1 metric and compare different selection methods. Selection with an oracle yields the best results, surpassing the performance of the generator. Self-selection surprisingly performs better than the generator, indicating the importance of careful supervision model selection in practice. Section Summary. In this section, we explore the quality of synthesized data by using a transformer to solve arithmetic tasks, focusing on predicting eigenvalues of symmetric real matrices. We find that while increasing the number of beams in beam search does not necessarily improve accuracy, evaluating multiple candidates can significantly enhance prediction quality. By incorporating external supervision through a verifier, we observe improvements in model performance, indicating the importance of careful data curation for enhancing synthesized data quality in machine learning tasks. Section: Discussion and Limitation. In this section, we explore a new problem concerning synthesized data: how to avoid model collapse by selecting data effectively. We suggest using feedback from a verifier to strengthen the synthesized data. It's important to not only focus on the generator's quality but also on having a reliable verifier for data selection when training new models with synthesized data. We analyze the impact of the generator and verifier on the final model's performance, assuming a linear model and Gaussian mixtures. Our experiments in simulation, mathematics, and news summarization show that using a good selector for data selection can prevent model collapse. Our work is crucial in the age of large models and increasing use of generated data. One limitation is that we only looked at data selection for data curation, while other methods like data augmentation and weighting are also important. Exploring broader data curation methods to prevent model collapse is a future research direction. We didn't consider the effect of prompt engineering on the generator in our experiments, which could improve generation quality and benefit synthesized data. We thank our colleagues for their support and discussions.